And we are going live. Okay, in theory we should be live. Hey everyone, welcome to another live interview here on my Universe Today channel. This week, I'm pleased to bring on a special guest to talk about sampling the solar system. Talking with Justin Simon from NASA. Justin, welcome to the show.
Thank you. It's a pleasure.
So the question I always ask people, who are you? What do you do?
Yeah, so I am a scientist at the Johnson Space Center, and in my day job, I lead a group of scientists who work with rocks. Typically, these rocks are from outer space or from extraterrestrial materials, but we also work on rocks from Earth, and we're largely chemists or geochemists. We also call ourselves cosmochemists, and we determine sort of the way that these rocks formed through the chemical record. And we also use geologic and geochemical and geochronological constraints to put these processes in temporal sequence.
So, I mean, the tools and techniques for figuring out how old things are here on Earth are different from the ones that you'll use across the solar system. So, like, what is the main method that you figure out how old various structures are here on Earth?
Yeah, so that's a really good question. And there are essentially two broad concepts of time that we use. One is relative time. And so a lot of that is observational. We evaluate what is on top of or what is outside of and versus what is below or inside of a certain texture or a certain geologic outcropping that we're studying. And then we infer that the order is the older on bottom and then the younger is on top. Sometimes that gets inverted in like a river channel or something like this, and that's when we have to really carefully evaluate the geologic context of the terrain. The other technique, which is largely a laboratory-based technique, is to determine the absolute age of the sample itself from that outcrop or from that geologic feature. And we do that in the laboratory from a myriad of different ways, oftentimes extracting out certain elements and looking at radioactive decay between parent to daughter isotopes, sort of like your uranium to lead or these isotopic systems. And we use more than one system ideally to evaluate the age of formation, or most rocks have more than one age because they're not determining just the formation age, but first the formation age, and then the reheating and deformation age, and then maybe a later alteration of that age or something like this. And so, but using those various different tools that are all based on elements, so therefore they're all based on chemistry, those chemical behaviors linked with those ages can tell us something about sort of the absolute sense of how that rock's history proceeded.
That's interesting. I didn't. So if I pick up, say, like a metamorphic rock, you could not only figure out when it turned into its current form, but even its earlier lives.
That's right. Not always. Sometimes it's just too disturbed or too metamorphosed, if you will, and everything's been reset. But we have the ability in almost every common rock to extract some vestige of the history of that rock from its very beginning to when we sampled it from the surface. And actually, for meteorites, this is really important because we're looking through a really traumatic event that is coming to Earth through our atmosphere. And so, the outside of it and potentially the alteration on the surface of Earth in a desert or even in Antarctica where it's cold most of the time, ice cold, right? We still have to see past that latest sort of superficial event. Sometimes we get really lucky and we have little exotic or little remnants of an earlier history of that rock as a little relic, and they may preserve even the textures and original minerals of that we call protolith.
So So, I mean, people are generally familiar with the idea of, say, radiometric dating, carbon dating, things like that. But I want to focus specifically on the techniques that you use to date the oldest objects, the things that are in the age of the solar system era, the meteorites that you do. So let's say that a woman in British Columbia comes into the lab because a meteorite has fallen through a roof next to her. So you've got a fresh sample of the solar system here. What do you use? Which methods do you use to try and figure out the age of that sample?
Yeah, that's a great question. And I'll just reiterate, not to make a major tangent here, but the reason that we are doing sample return missions is even that fresh sample isn't fresh. Yeah. Right? It went through the roof, it went through atmosphere, et cetera, et cetera. So it has been, disturbed, if you will. But I'll just assume and ignore those features. If we're really looking at the antiquity of that rock, and a lot of the geologic processes that may be different in age, that far back in time, we can't really resolve easily, right? We have, geologic processes are, thousands to tens of thousands of years long events. But when it's 4.5 billion years ago, the resolution of our chronometers are such that that's within uncertainty. But nevertheless, we have two primary radiometric systems that we use: the uranium lead system, or the uranium thorium lead system, and then the argon argon system. Those are very different elements. One is based on lithophile elements. One is based on noble gas, and those again have chemically different behavior. And so the gases, if you have a little bit of a heating, those gases are released, and it's sort of a resetting of that event. Whereas in order to reset the uranium lead, or the uranium thorium lead system, you really have to heat it and affect it significantly more. And so, anyways, if those two ages were what we call concordant, or the same, that would give us a lot of confidence that whatever events happened to this rock in its past are within error, mm-hmm. And the error can be quite small. In the best labs on Earth, we're talking only a million years or so, right? But that's a part in 1,000, or part in even fewer or more than that for a 4.5 billion year old rock.
So I mean, you mentioned like a couple of techniques there. I mean, do you still want to go for multiple methods? Is there one that is fairly, like, if you could only do one test, if I gave you a meteorite and you only got to do one test, which would be the test that you'd do?
Yeah, it's a good question, and there are other techniques that I didn't mention. Yeah. I mentioned those two because they are the most commonly used, and in part because they have, and not to say that there's a hierarchy to our systems, but they sort of span the range between sort of robust, most difficult to reset, versus more easily reset. There are some more easily ones reset, but they're so easy we don't usually use them for old rocks because it's kind of a little bit pointless.
Right.
But then the other thing that you're getting at is not just the isotopic system or the elements that we choose, but how we go about measuring those elements. And so there are methods in which we are using like a focused beam, whether they're an ion beam or an electron beam or some type of laser, to extract out a targeted region of the rock, versus taking that rock apart, kind of like basically pulling apart the constituents and then working with those constituents in a chemical processing sequence in which we can extract the most precise and accurate measurements for those individual components. One is allowing us to get at much smaller spatial scales and without handling the rock as much. And whereas the other one, we have to really, we have to decompose the rock into its constituents, and we have to pull them and sort them into their different minerals typically, and then chemically digest those, and then separate out the elements, and then characterize them. And so these are different techniques, but in combination, they tell you somewhat different things. So for example, with the in situ techniques, we can go that is smaller minerals that are not commonly large, And oftentimes those have the greatest ability to have their ages determined because of their chemical composition. And so that's one approach. But then in the other approach, where you're decomposing the rock into its constituents and then and measuring those larger major rock forming minerals, we can then be confident that whatever age we determine from those constituents are really important for the entire rock. And so then when we combine those two different approaches, those ages, or compare, I should say, those two ages, then we can also get a sense of how robust or what is the geologic history of that rock. So for example, you could have one of these small minerals that forms really late if you had an igneous rock or a metamorphic rock, in the sort of sequence of that rock solidifying or dropping below the temperature in which things are mobilized, elements are mobilized in a metamorphic rock. And that would, if you looked at the major elements, the major mineral phases to determine that age, and then you looked at those later forming accessory minerals, and they were the same, the entire temperature interval in which that rock formed from sort of the first minerals to crystallize to the last minerals to crystallize, you could determine the age span. And maybe it's the same age within resolution, or maybe it's 10 million years or something, or you can evaluate that. So you have, again, another way.
Right.
Sort of
so you'd want two. So you'd storm out and go, no, I need two. But so we've talked about this idea, and this work of like taking a sample, putting into a beam, or taking the rock very carefully apart into its constituent minerals and then sample each one. That sounds very complicated, very sophisticated machinery. So now I want to move to Mars and look at some of the most incredible robots ever built, and yet they are not laboratories of that complexity on the surface of Mars. So as a geologist, how do you attempt these same kinds of tasks using the tools on hand that you have on, say, Perseverance?
Yeah, great question. And it's right down the alley of what we're trying to do. So we have a combination of instruments on the rover that allow us to do the relative age determinations, or the geologic context and relative compositional differences. Some of them are we can get quite accurate chemical data, whether it be elements, inorganic elements, or organic elements or compounds. We cannot do the age determinations yet, but that's part of the sample return component, right?
Which we'll talk about in a second.
What we're doing now is we're prioritizing which outcrops and which geologic units and which terrains provide the most leverage in terms of understanding the geologic history of the crater and the area eventually, hopefully, outside of the crater. And then we're being parsimonious about this. We're saying, okay, we'd love to sample all of those rocks in this hillside, but that one, we can extrapolate it to the delta. We haven't talked about that, but there's a delta. We can extrapolate that to these other lower features, and we can basically say, this is an age that's older than those rocks, and it is younger than those rocks. We don't know what the age is, but we know, relatively speaking, how it relates to those rocks. So when we bring back that rock to Earth and we study it, then we can really tie in. So it's all about being strategic and prioritizing the sample cache, and that will maximize our science return on Earth.
That's really interesting. So in other words, you're building the chronology, but with question mark for all of the actual dates of when these things happened. But then if you get that one sample, it's the key that'll unlock the whole stack.
Yeah, and it's probably more than one, right? But you can see how we can, we don't know how this sequence of the geologic history relates to this sequence, but if we can determine this age and this age, now we have an absolute tie line that we can relate. So even if we can't relate them in a relative sense, once we get that absolute rock age, we can then put it all back together.
That's really cool. So I mean, when I think about the kinds of geological structures here, say you've got sediments that are forming over certain periods of time, we know fairly accurately how long these things take, how long this, say, glacial till took to form, and how long this river sediment came together. But when you see similar features on Mars, can you make assumptions about how long these things took to form, or is this sort of part of the question?
It's a really good question, I think that people have experience looking at Mars and trying to understand the history of Mars, and that's mostly based on observations of the sorts of geologic terrain that you were just describing and relating it back to Earth. We also have the ability to determine relative ages by looking at the frequency of crater sizes and abundances on surfaces. That's a relative chronology. But on Mars, we know we have a very different scenario. That is, on Earth, where we have plate tectonics and things are reworked and we've lost all these ancient terrains. On Mars, you have these terrains that have lasted. You maybe had that geologic event, that landslide or that lava flow or eruption, but then you have 2 billion years or more afterwards where it's just there. And so, all of my field experience is from Earth. And so when I first started working with the Mars team, the Mars rover, and looking at the surface of Mars and seeing actual rocks, one of the first things I was struck by is how I had to recalibrate my eye to say, okay, that's a lava flow. That's what it looks like after 2 billion years of weathering or surface, processing. A lot of it is wind-borne physical, erosion, if you will. And I'm still trying to get my eye calibrated to that.
So we're not going to have a flow that's 2 billion years old here on Earth. They're all gone. You only get the ones that are a couple of thousand years old.
We do have some, but very, very few rocks that are. I mean, we have no rocks that are more than like 3.5 billion years old. No landforms. There's some, like I was talking about, these exotic clots or relics of grains or what have you in some of the ancient terrains, say in Australia, where we can say, oh, there must have been a continental crust, or there must have been some crustal material 3.8 or 4 billion years ago. But it's not like we're walking across a rock, a sequence that's that old. Whereas on Mars, everything's old. That's not true. I mean, some of the stuff is being blown around today. So you do have some regolith and some dust building up and other things that are certainly younger than that. But the rocks themselves presumably are at least 2.5 billion years old. And some of the rocks we're anticipating to run into could be older than 4, especially outside of the crater. And so that's really, really old to have a rock, surface. And that's really exciting, because that's just to kind of back up a little bit, if we again take our understanding of Earth and sort of inject it onto Mars, 3.5, 4 billion years ago, that's when some of the first life began to form on Earth, based on the fossil record. I should say 2.5 to 3.5, that range. And on Mars, what we know is that the climate changed somewhere in that same time period from probably what we would consider habitable, so it's warm enough and there's enough water, humid enough that you could support life, to one that is currently today very, very harsh. Not that you couldn't have subsurface, niches or environments where organisms could live, but certainly at the surface, super dry, and very cold. And so, anyways, my point being is that in this time period, this isn't an accident. This is by design. We went to this area, right, because we were, it's sort of a cross section of the right sort of. We have a delta lake, shoreline type of environment of this age, with the anticipation that we would likely, or more likely, stumble upon, if you will, environments that could contain, evidence of life, biomarkers, or at least have the potential. Is the main point. So we have the potential to be in that time and sort of geologic, ecosystem, if you will, or I should say environment. Eco is kind of implying life, but
yeah. but it is interesting to me that in looking through the terrain on Mars, you are seeing these features, as you say, rocks that are 4 billion years old, features that are much longer lived than we have on Earth. And so, in fact, not only can we, hope to discover if there's evidence of conditions for life on Mars, we can learn a ton just about what earlier Earth might have looked like, because
Yeah.
you've got you can see, as I said, like what happens to a lava flow over, over billions of years as opposed to thousands. That, like, a
Yeah.
fully formed flow, right? As a, in its
Yeah.
full structure. That's really interesting. So, okay, so we're sort of building towards this. So then the next step, I guess, is, the story of the Martian rovers is, of course, the search for past evidence of water, leading up to potentially the conditions for life on Mars, either today or in the past. So what will Perseverance be looking for in, like, what are going to be the, because you only have a small number of samples you can collect. So each one is going to be very precious. So what are you hoping, like, what kinds of things would you see and go, oh, let's sample that, please?
Right. Yeah. So we don't anticipate stumbling across, a stromatolite or some
Right, or
really
a
super,
fish
super
fossil.
obvious
Yeah.
fish fossil, dinosaur bone. We're not going to trip over that.
Yeah.
Right. But if we did, we would know how to sample it, and we would bring those back. We don't have any instruments that say life, right? That's not that we don't have any DNA measurements, and maybe DNA wouldn't even be useful. We don't know. But we do have an array of instruments that are next generation, in the sense that they are tuned to look for mostly geochemical, but also looking for image features that would be indicative of biosignatures. And so your question is, how would we kind of like sort through this haystack to find those samples that we really want to get at? And again, we're using our geologic intuition. So
Right.
we aren't going to go.
Yeah, so that's what I was guessing. It's like I'm assuming that you're going to see it from a geologist standpoint first, to just make a decision on where you're going to lick a rock.
That's right. So we spent during the cruise stage, when we knew that the rover was on its way and it wasn't just standing on the rocket waiting to be launched, we had a series of strategic planning sessions where we, using remote observations, largely from the Mars reconnaissance observer, where we're seeing digital elevation, and we're seeing some kind of mineralogical signatures from spectral data. We were able to work out, and people have been doing this a lot, but we were focused specifically in the area that we were going to identify the sort of highest potential places that we wanted the rover to visit. And so we put together a series of high priority targets, and then we spent time connecting the dots. Do we have the time to make it, with our expert engineers, rover driver planners, who have an algorithm for calculating how long it would go over that kind of terrain versus going over this flatter terrain, and this type of thing. Basically identified how we could best, like in a constellation, right, from stars, how we could best reach those various high priority targets. Of course, everything changes when we hit the ground, because we didn't know exactly where we were going to start, because that was an automated process where it was avoiding hazards. We were going to a really exciting area that has hazards, but we didn't know exactly where it was going to land us. And so it landed us to a certain place, which I was super excited about, a little further away from the delta, but that was good because it then allowed us, kind of forced us to study more than just the delta, sort of like the crater floor and leading up. Not that we wouldn't have, but this really provides a richness, a wealth of that earlier history. And so then when we got on the ground, we're doing the same type of thing, where now we have a starting point. And so we're saying, okay, well, those rover traverses are out that didn't start here, that started way over there, because we're not going to go drive for 100 days over there to then start, right? And so then we put together new rover plans, and we're constantly updating these. And we have a notional list of those sites, and we have a notional list of the types of samples that we'd expect from those sites. And your question really was, from the sample perspective, what types of samples were we looking for? And so, again, we're using our geologic intuition, or geologic experience, And I'm not the most experienced sort of astrobiologist on the team by far, but I know something about what we're looking for. And so we're looking for units, for example, that might be at the bottom of lake beds that are fine grained and have clays, and are where these types of microorganisms might have been able to live. Obviously, the delta itself is, if you've looked at current deltas on Earth, I mean, not natural, where like in Alaska, where you're seeing the ribbon of the rivers kind of coalesce into a body of water, you can see it being reworked again and again and again, and these stages of the delta and the sediment being redistributed. It's sort of in a sprinkler sense, going back and forth, and within that you can see, and on Earth you can see the kind of pastel yellows and oranges and reds and greens that are these microbes. And so that's again using our this is now not so much geologic but like ecology intuition, that those delta units and specific layers, the finer grain layers, will retain evidence of those organisms. And so we're looking for fine grain sediment. Obviously, we're looking for anything that's got organics in it. We have the ability with our instruments that have spectrometers that can, that were not spectrometers in the mass spectrometer, but looking at spectral light or various types of electromagnetic light, looking at Raman signatures and ultraviolet signatures that can determine specific organic molecules and what have you. So we can say, okay, this layer is organic rich, this layer is not. Well, we're going to go for the one that's organic rich, right? Once we've geologically defined that, we can't do any of this before we get to Mars, right? We can say, okay, there's the delta, there's the bottom of the delta, but now we can drive up and we can use those instruments literally to scan over those beds and say, okay, this is the layer that we want. We're still in the search of that layer. We've just started.
Right.
But those are the types of things that we were looking for. Another thing that's really interesting about Jezero, and another reason why we went there, it was proposed to go there, and then we finally decided, was the presence of carbonate. Carbonate's really common on Earth. It's fossiliferous often on Earth, not always, but it's got a large amount of carbon or carbonate on Earth is related to the carbon cycle and related to life. And so, being able to go to a place where we identified carbonate from a remote from orbit, or from Earth even too, where we can then go and look at those units, that will be another place to really focus on. We're just actually pulling into an area that may have some carbonate. The main carbonate deposits that we think are actually at the margin of the crater, and so we won't be getting to that for maybe 100, maybe 200 days.
So what would a deposit look like? We're building a new house, and so we've got a lot of earth moving equipment around here right now, and it's interesting. We're sort of seeing places where previous people buried organic material, and so we're seeing deposits of old tree material, but it's essentially now it's just like a dark layer that gets unveiled as the excavator is pulling out a chunk of dirt. And we know that in the past someone sort of turned stuff upside down, and we're seeing this material. So like what would be the cause of a deposit on Mars, and what would it sort of look like to Perseverance?
Yeah, it's a really good question, and there are a couple factors that would play into what it would look like. The main thing would be the amount, the composition. So I don't mean the carbon necessarily, but I do mean the carbon content. So oftentimes it's not just carbon, it's not graphite, although your tree trunks will eventually become graphite if they had time to get buried and baked. But it's the combination of elements, and so that will play a role. And so in terms of our geologic setting, generally speaking, we have an inlet channel of material from a watershed that's pouring into the crater. We believe that there was a lake. Maybe the lake was a transient lake, that sometimes it dried up. This is what we're really excited about understanding, and that change of lake level and drying and filling again. Those are all really great environments to sort of generate ecosystems or niches that are habitable. Anyways, depending on how the river history and one of our most recent studies that we published very recently in Science showed so there was events that were sometimes flooding events were bringing material into the crater floor, and so those would dictate how diluted the carbon signature would be, depending on what material was being brought from the watershed. So the water itself is carrying nutrients and carrying sediment and carrying material into and then depositing into the crater. Sometimes into a lake, we think, and then sometimes maybe no lake, but as rivers into the various channels, which they could be more concentrated. And so that would determine sort of what they like, the concentration of carbon, of the nutrients or the materials. The other thing that would play to your question is how much burial occurred. And so, if we are, and we're not certain exactly where we are in terms of the ultimate depth of burial, we may be pretty close to the surface, and so then these rocks have not experienced a lot of overburden. But the overburden, that will determine how sort of metamorphosed or even just altered rocks will become. And so, when you see fossilized material, in sort of planar rocks, oftentimes that's a combination of the pressures and the fluids and the temperatures of those fluids that have come through. So that's a long-winded answer to say that it's basically what if you're thinking about it in your kitchen, it's what parts of the recipe, what ingredients do you have, and then how do you bake it, and how do you stack it, and so dark material tends to be organic, but you can also get iron that becomes dark, right? And so that would dictate how things look.
Right.
That's a long answer.
Yeah, no, it's fine. It's fine. I mean, it's like, I think, as I said earlier, you only have 36 samples that can come home, and so each one has to be chosen very carefully, and so I just imagine just all of this geological experience coming to bear to just kind of go there. So you've got to this point now where you've chosen, you see something that looks like fine sediment that is laid down on from a flowing river or maybe some ancient deposit. How would you even choose where within that sedimentary level? I'm assuming you're seeing it from the side. So how would you choose, like, how thick is this going to be, and how would you choose where to actually drill to get what you need?
Yeah, it's a really good question. And I just wanted to add another thing, and a big part of what I would like to think that I'm contributing as a team member is not just which sample, but actually which suite of samples. And so, I was getting at before, we could use this sample because it stratigraphically is constraining those below it and those above it, right? And it's the same thing for whether it's a geochemical observation rather than a geochronological observation. If we can constrain effectively the samples that we want in the delta, and look at the carbonate cement in them, for example, we would like to be able to compare that, because that tells us something about the chemistry potentially of the water that was in the lake at the time that the delta was forming and what have you. We would like to be able to compare that to other examples in the geologic history of the crater fill that might get at the chemistry of water in the crater. So, so here's an example of a suite of samples that are hypothetical. If we found an older, whether it's, we could determine its absolute age in the lab or even just its relative age through, relative position, and say, okay, here's a carbonate or here's a cement that we know is the most ancient, and it has this composition, and therefore we can extrapolate what kind of water chemistry was interacting with that rock at that time, filling in the pores, like your hard water in your bathtub, relate that to the same type of minerals that are forming in much younger, much being, we're not exactly sure, 500 million years maybe, or maybe more, ones in the delta, we can then look at the changing history of the water that was in that lake. It may not have been a constant body of water, but that history and that change, whether it's being more alkaline or it can be more acidic, these types of environments and these compositions are more or less habitable, and also they are, at least on Earth, it's not always the case that one is habitable and one is not, but it's the type of organism or the type of biochemistry that needs to go on for that organism to live. And so those types of things are really interesting to us, because it's if you know what the water chemistry is, you can kind of infer like what kind of organic chemistry of an organism, kind of charge transfer, if you will, or what have you, is needed to live in that environment. You do have to spend all your time protecting yourself from the acidic chemistry, or not, and you can open yourself up, and I'm personifying these microbes, but get nutrients in a different way. And so those are the types of samples we would be interested in pairing.
But it does sound like, again, always in the back of your mind is that you've only got, like, what's the total number of samples that you're going to be able to in a future return mission? It's like 30-ish, right?
It's in flux, but we have a total number of tubes, and so that total number of tubes is just over 40, but we expect sort of our working number is like 30. Yeah,
right, because some of them are sort of like filled with samples, controls from Earth.
Well, that's in addition to some of the blanks, if you will, or the background. But what we're doing, at least currently, is that we're planning to, in the Jezero area, that's the name of the crater, we're planning to collect about 10 individual samples that we are going to pair. And so we're actually getting 2 tubes. And then we have a little bit more to get, a couple more samples that we don't have. We're not going to pair. But because we have these 2 tubes, we're actually going to have, the plan is, this may change, but the plan is that we're going to stash or cache a subset, one set of the pairs, at a place before we embark on the next round of the extended portion of our mission. We would carry one set of those pairs with us, and then leave this pile, not exactly a pile, but leave in an area this first round of samples. And so anyways, we may be able to go back and get all of them. People are talking about, what if we had 2 we're planning to get 1 cache. That's the Mars. When I say we, now I'm talking about the big we, the NASA we, United States world we,
with
not Mars 2020 we.
Yeah.
But it may be that, it would, I'm just telling you what I think. This is not a NASA level decision, or what have you. But if there's a second cache that is left there, that has been thoughtfully put together, it would make a lot of sense to go back and get that one too.
Yeah.
Right. Because even one, there are a lot of us scientists who would be super excited to have that sample that comes back. We're not all going to get. There's going to be a lot of sample, relatively speaking, compared to what we have, because we have none. But going back, getting all the samples would be ideal.
Of course, yeah.
But that all said, we have to, like you said, we have to prioritize. And what we have the ability to do, and what we're doing constantly, is that we're documenting the samples. And this is part of what I'm doing, and what my colleagues that are focused on samples are doing, is sort of documenting the samples in enough detail that we'll be able to intercompare them as we march along and as we collect more. And then eventually, when we're in a situation of the next collection of the cache, we'll say, okay, we want 1, 5, 7, 8, 12, 14, 32. Those are the ones we have to have back, right? Because because we've documented all these observations, they are tied to the geologic history. In this way, they're a diverse suite. They provide maximum science when brought back together, that type of thing. And so, documenting what we have and what we don't have is part of the game.
Right. But obviously, as you say, there's going to be an extended mission, and so they're like test tube size, these samples, right? And you've got about 30-ish. That number is in flux, as you say, and they are going to be extracted, deposited on the ground, or are they going to be held on the rover They're going to be cached.
So they're currently held in the rover. So just to be clear, we have about 40.
Yeah.
We're thinking that we're going to be able to bring back 30. So
Right.
we're going to leave like 14 or so in the first cache, and then we'll take those pairs and then continue to collect more as we go on. And so at the end, we would have one cache that's got 30-ish and one cache that's got like 15-ish, something like this.
Right. Right.
If you're counting the blanks and what have you.
Right.
And so the way it works is that we have a bit that drills into the rock, and then ideally, if it doesn't fall out like it did in the first time,
or crumble into powder.
Crumble into powder. Right. We then we take a picture, make sure it's in there, looks good, seal it, and then that same arm holding position then sticks it basically into the belly of the rover, and it gets put into this chassis, this carousel of samples that have tubes that now are filled, and we'll carry those. We could carry all of them, but because we're carrying all those tubes now because we went in and grabbed a tube and brought it out to drill, right? And so the idea is that we would leave whatever 15-ish in that first cache around that could be fetched and gathered up and brought home, and then we'd carry the pairs and then collect the rest. And at the very end, in 6 or 8 years from now, 4 Martian sols, years, or 5, depending on how you do the math, we would, if we were to drop the second cache, we would then just pull everything out that we have and put them out, and then folks all over the world are working on this next stage where they have a so-called fetch rover that has the ability, will have the ability to go in and then say, okay, I'm going to take this tube and stack it, and this tube and stack it, and this tube. It has to be able to kind of vacuum up, if you will, but in a very precise way, because I don't want that tube, I want this tube, and collect the ones of that final bit that we would bring back. And the total number, as you say, is probably in that 30-ish range. I mean, obviously, if everything goes well, the qualified life is not as long as is the end of the second extension of the mission. But if the Mars, Science Lab is a key to the past, we have a fantastic rover, right? And we should be able to continue going. Who knows? If a tube gets jammed in our bit, then we're going to be sad.
Yeah.
And that's why we'd have that first cache. If that first cache was there, even if we went for the second, we'd have that first cache, and that would return.
And I mean, when I think about Spirit and Opportunity, both rovers were, their initial missions were for 3 months. They lasted for, we think about Opportunity, like a decade. So do you foresee, is there a way to do sample collection after the tubes run out?
No, but we can do science. Assuming that the rest of the hardware works, we can, we still have the ability. We'd have to kind of like relax some of our contamination control constraints, but we could still continue to abrade. Our abrading bits will of course get themselves abraded, worn down a bit, so they'll become probably less effective. And hopefully, everything is gonna start to degrade, because that's why we have a qualified life. It's not one life, but different components have a longer life. But if the past is the key to the present, many of our instruments and our cameras and things will continue to work, and we can continue to do science, really effective science, after all the sample tubes are used.
But I guess I'm
would be
envisioning
like we're doing now. So
could you? Until the bit actually abrades to the point that it's not able to actually drill anymore, couldn't you extract samples, just deposit them down, mark them with the GPS that they're there, sitting on the surface of Mars? And although it wouldn't be as pristine, I guess the worry that I have is like, if because Curiosity and Perseverance have this RTG, they can run for a very long time. And I can imagine that maybe the best is yet to come, that you go through your initial mission, you find all the samples that looked good within the mission parameter, and then 5 years later, 8 years later, Perseverance runs across like the perfect rock, and you make a sample, and even though obviously leaving a chunk of rock out on the surface of Mars for 3 years while the next collection mission is put together, is suboptimal, there would still be some. Like if I gave you a chunk of rock and said this sample is taken from the surface of Mars 5 years ago and sat on the surface for 3 years, do you want it? And you wouldn't be like, nah, just throw it in the garbage, right? Still have
Right.
value.
Well, so I mean, the future is hard to predict, and this is one of the most debated and important issues that we deal with now or later, right? And so we have these sort of this trade space where we're competing with. We have a bird in the pocket now
Yeah.
versus what we could get later, and we have a lot of smart people thinking about this, and they're pushing against each other a little bit in a good way, right? We have the scientists that are saying these are the scientifically most compelling things, and then we have the engineers that are saying, yeah, but just remember, right now things are working great, but if you kind of like extrapolate our models, this and this is when things may not work. And then there are the realists that are like, and when we fall off that small cliff and just slightly lodge that tube into the builder, and then we can't use it again, we're done, right? So you have all these worry warts, and then optimists that are kind of like playing into each other, having this conversation. And so I mean, literally, we just had this science team meeting the last 3 days, and one of the big questions is that here's our notional cache. We have to sample every 70 sols or 70 days in order to do it, and sometimes it's not going to be the best sample, right? But if we don't sample now, we're not going to get those samples back when the Mars Sample Return mission is collecting them, because we will not have collected them in time. Because the collection itself is not a single afternoon thing like it would be on Earth. We actually have about 10 days sort of minimum in our sort of our normal sample sol path, we call it, where we're basically targeting this is after we decided to sample, right? This is the unit, right? So then we're like targeting the outcrop, and then we're refining that target and taking the sort of the context images that we need to then position the different instruments. And then we are making those instrument measurements, then we're abrading it and saying, okay, verifying, this is what we're looking at, backing up, and then we have to move a little bit over and then actually taking the core. And all those things, of course, are interlaced with days where we're giving it instructions what to do. Some of it's automated, but then it's downloading and showing us, okay, there was no fault, it was successful, and we kind of do this. And so each sample, just collecting a pair of samples is an 11, 12 day process. And then if we have any questions like, oh, I really think that that maybe if we looked at the inside of that borehole, we might learn a little bit more, and then you do a little follow-up measurement or what have you. And so and then we have to drive to the next place, right? And so in order to fit all that in is part of our calculus.
So we've only got a couple of minutes left, so I just want to give sort of one final answer, which is sort of the point of this whole process. So at some point in the next, say, decade, ESA and NASA put together their sample return mission. The Chase rover grabs the samples, puts them into the return rocket. The samples are returned to Earth. They arrive on Earth safely, and they are distributed to scientists around the world to go to work to finally get their hands on pieces of Mars and potentially a place where life could have been in the past. What would be the thing that people would be looking for? What would be the slam dunk as you looked through those samples? And obviously, a chunk of fossil, a chunk of would be great, but more, something that's realistic. That's more realistic, but would also say, yes, definitively there was life on Mars in the past.
Yeah. So I think that this obviously is the most important question and a really good question. And I think that we should look at it through the eyes of how we look at ancient terrestrial rocks and look for life, right? And so we don't just take one sample and have one person look at it and say, yep, yes, right, with their one technique. And what we do on Earth is we have a bunch of folks using a variety of different techniques and combining those observations to come up with a case for it being life. It's not just a little squiggly texture. That squiggly texture actually has an alignment of minerals and or has certain chemical constituents that require sort of an electron transfer process that is like the cell membrane, or you have, like I was talking about before, you have these organisms or these potential organisms in a rock that's recording a habitable water, right? So you put together these different various pieces to make that case. And ultimately, we will never know until we actually find an organism. And biologists are the ones who are going to be able to tell us, is that a microorganism or not? Or I should say a fossil organism. They degrade over time, of course, and they become more squinty, if you will. Some of my colleagues and professors when I was a graduate student spent a lot of time doing this on ancient Earth. But when you start to put together observation after observation after observation, when you're back on Earth in the lab, when we're combining chemistry and structure and interrelationships between, like I was saying, the water chemistry, making sure they have the nutrients that need, is the right type of looking organism that you have. Those are the types of observations that we would say, this is clearly a fossil microbe. And with a lot of the instruments, the resolution, the instrument or the technique is what we're doing on Mars. It's just really the resolution that we need. We need to be able to really refine that we have the phosphorus, that we have the specific type of organic molecule. Those types of measurements that are done in more sophisticated labs, some like we have at Johnson, but other places around the world, that will be used to definitively, in combination, like the chronology that I was getting at, where you're using multiple systems. Those multiple observations will then tell us that we have a fossil microbe.
And is there? I mean, it's really difficult to prove a negative, but is there anything that would definitively tell you our assumptions about Mars being habitable in the past are wrong, and that it never was habitable?
Yeah. So we can't prove a negative, but certainly part of what we know we can answer is whether or not we can determine whether we will observe habitable environments on Mars. Right. That is something that we can determine through the chemistry of the rocks, through the history that is laid down in the geologic record. We'll be able to search for those various different habitable landforms, and that's a big part of those of us who are more geochemists or geologists who are not biologists or not astrobiologists, if you will be focused on. One of the big things that I have stressed a little bit here, but would stress, is that we have more than just the crater to search. The outside of the crater has a number of other potential water, rich lakes, small pond, looks like fluvial channel, et cetera, and the range of rocks is like 2 billion years out there. And so through all these different environments, if we find zero habitable environments, when we look in detail, that will be pretty conclusive. But I think that we've already passed that already, mm-hmm. Right? We're in a crater where we see. Okay, maybe that was too strongly stated. I think we're close to sort of demonstrating that this environment that we have in the crater, grossly speaking, is one in which life could have formed. We have clear evidence for it, of this delta. It wasn't just something that looked like a delta. When we go up and look at the outcrop itself, we see the structure within the layers and beds of the being deltaic, meaning people have looked at these so-called bed forms in detail all over the world, and they know what the shape is and what the height is, depending on whether those grains of materials, sands, are settling through water, right, or whether it's wind. All those things have been studied in detail, and so we are very confident that this is a delta that was being formed in water, and so that, to first and zeroth order, is a habitable environment. So now we just need to find material that would record signatures of the chemistry and signatures of the organics, or of the actual biomarkers, which we haven't done yet. That's the next step.
Yeah, fantastic. Well, I don't want to take any more of your time, Justin. Absolutely fascinating, and it is a pretty exciting time to be uh, watching this space and seeing as we're in the process of eventually getting pieces of Mars back here on Earth to study, and maybe we can answer like one of the most important scientific questions that's ever been asked. So good luck if you
Thank
with
you.
your search, and let
I
us
feel
know.
very lucky and fortunate.
Yeah, and let us know if you find anything.
I will, for sure.
All right, thank you so much.
All right, take care.
Okay, great.